So fine, let's start this. So yesterday we have seen PMF. Okay, I hope you are good with PMF part. Okay, and also we have started the PDF part also, right? PDF for the continuous random variable. Fine. So here, if I just quickly erase this and show you, yeah, fine. So yesterday I was saying you that in PDF part, okay, in PDF part, we don't have the probability directly, right? We don't have the probability directly, right? So it's a probability density. Fine. So if you want to fine, so whatever you take actually, right? So whatever you take the area, right? So that is actually called a probability density. You can say it as probability, but technically it is called the probability density. So if you want to find out, okay, if you want to find out, okay, a particular value, okay, so probability of the random variable falling between -2 to 2, fine, what you are going to do, you are going to take the area between these range. Fine. And also we have seen, if you want to go for a particular value, you can use a small sort of thing like to calculate 2 to 2.20001. Fine. So as you can see, this is not giving the exact probability. Fine. It's not giving the exact probability, right? It is giving you the probability density. Fine. Over a range. Okay, even the range is very small or a very big, but still it is the probability density. But for practical purpose, you can consider this as the probability itself, because the change is very negligible. Okay, fine. That part I hope you are clear. Now now let's try to understand. Okay. Okay, how to draw the PDF. Fine. Fine, let's try to understand how to draw the probability density function. Okay. See guys, here there are two ways, okay, which you can consider PDF. One is parametric, other thing is non-parametric guys. Okay, one is parametric, other thing is non-parametric. So see, I'll tell you one point. Yesterday Karthik asked this question, so which is actually important question for you also, Meghana. See, now the question is, we are having, when we are having discrete variable and when we are having continuous variable, fine, and for discrete we are having probability, uh, let's say discrete distributions, okay, and for this we'll having probability continuous distributions, okay, just simple words, fine. Then for all the discrete variables, okay, for all the discrete variables, can't we have only one function, I mean one type of distribution? Okay, for all the continuous type of variables, can't we have only one type of distribution? Is the question clear, Meghna? See, these are discrete and continuous, right? So for all the discrete type of variables, can't we have only one type of distribution? Why so many distributions are needed? Okay, if a variable is continuous, can't we have only one type of distribution for all the continuous variable? Why do we need to have all these type of different continuous distributions? Fine. The answer is, when you say discrete, it is discrete, but inside discrete there might be different type of discrete variables. Okay. When you say continuous, it is continuous, but inside continuous there might be different type of continuous variables. What does that mean? There might be a specific continuous variable which might be increasing for some time, having a peak, again decreasing for some time. Okay, there might be a particular continuous variable which might be always increasing. Okay, there might be a particular continuous variable which might be in the form of this. Okay, see, all these are continuous variables. Okay, all these are continuous variables, and obviously all these distributions will be called as probability density distributions, okay, or probability density functions. Agree? All these are continuous variables. Fine. But the nature of each continuous variable is different. Agree? So this continuous variable is having a particular nature. Fine. And this continuous variable, as you can see, it is continuous, but its nature is different. It's always increasing. Agree? So that's why you cannot have one distribution for all the continuous. Fine. So for this type of nature of continuous variable, we will have normal distribution. Okay. For this type, let's say we might have some exponential. For this, we might have some log. Agree? So even though all variables are continuous, okay, there might be difference between the nature of the continuous. Fine. So that's why you need to have different distributions for different type of continuous variables. Is it clear, Karthik and Meghna?
Yes, sir, clear.
Okay, fine. So that point which I've just mentioned is useful over here. So now, if you see here, when we are discussing a probability density function, obviously we know that we are dealing with a continuous random variable. Fine, that is established now. But inside that, if you want to try to draw a probability density function, okay, first of all, if you want to draw a probability density function, we don't know, okay, we might know or sometimes we might not know what type of continuous variable it is. We just know that is a continuous, but what type of continuous, whether it is a constantly increasing or decreasing, or it is having any slope, or we don't know. Fine. So because only if you know what type of continuous variable is that, right, you can try to understand something about the distribution. Okay, whether that will be becoming a normal distribution or Poisson distribution, or whether it is chi-square distribution, logistic distribution, what type of distribution you can assume. But if you don't know, like if you don't know, find what type of continuous variable, there are two ways how you can draw the PDF. Okay, one is parametric, other thing is non-parametric. Fine. So let's see parametric. Parametric is, here it's simple. What happens over here is, here we assume, okay, we assume that the underlying distribution, okay, we assume that the underlying distribution is some sort of known distribution. Okay, so we assume the underlying, because we can have a look at the data. Okay, we can have a look at the data, and let's say we use histogram. Okay, and based upon that, okay, based upon that, we will assume that, okay, this will become, this might be similar to a normal distribution, or this might be similar to a Poisson distribution. Okay, that is parametric. Okay, which comes under parametric density function. And what does parametric density, sorry, parametric density estimation, okay, PDE. Okay. What does parametric density estimation will tell you? Parametric density estimation is a method of estimating the probability density function, okay, of a random variable by assuming that the underlying distribution belong to a specific parametric family of a probability distribution, such as a normal, exponential, Poisson distribution. Okay. See guys, it's not that difficult. See, let's try to understand. Parametric, this is a concept, okay, or you can say this is a technique. Fine. So we want to, fundamentally what we want to do, we want to come up with a PDF. Okay, we want to know the probability density function, okay, for the given continuous variable or continuous random variable. Fine. So in some cases we follow parametric method. What does parametric method do? Parametric method is a method, okay, of estimating the probability density function of a random variable. That's fine. But how? By assuming that the underlying distribution, okay, we don't know what type of distribution that is happening over there. Okay, but we will assume, in parametric we'll assume that the underlying distribution belongs to a, okay, specific parametric family of probability distributions. Okay, what are those? Some famous PD functions. Okay, sorry, PDF functions. What? Normal, exponential, Poisson, just like we have seen the above, right? So we will assume, okay, based upon some observations, okay, we will assume, hey, this type of continuous variable, okay, might belong to normal distribution, okay, we'll assume. So then it's called parametric, okay, based upon some parameter we'll assume that the underlying distribution, okay, belongs to some famous parametric family, okay. And then once we assume, okay, that this is belonging to, let's say, normal, fine, then obviously we can use all the formulas that are applicable to normal function, that are related to normal function, to our function also. Agree? So you will see how we can do that. Okay, so let me show you. Yeah, for example, let's say in parametric density estimation, fine. So what we are doing, so let me just run this. Okay, so here okay, so I am creating a distribution, okay, I am creating a distribution, okay, let's say I am using the normal from the numpy. And when you see this one, right, so this is the loc over here, okay, is the mean, okay, loc is the mean, just a second. So the loc is the mean, okay, mu, sorry, scale will be the standard deviation, okay, and size is the sample size. Okay, this is a sample size. Okay, so now fine. So now if you see, we are trying to create, actually what we are trying to do over here is, see, we'll try to understand. We are taking a size of 1,000 sample, okay, from a population with a mean of 50, standard deviation of 5. Okay, these are population parameters, guys. Okay, so I hope you remember the concept of population and sample, right? Population and sample. Okay, what is the difference? You can simply say sample is a representation of a population. Agree? So if this is a population, fine, you can have a certain portion of this as sample which will represent this in all required situations. Agree? Because we cannot work on the whole data set, we will take a suitable portion of data set, a subset of this population, and we'll call it a sample, so that it will represent the population. Okay, so now here when we're doing this, what's happening? Okay, but when I say that sample is only representing, right, it is not the exact as population. Fine. So here also, if you see, we are trying to take a sample of 1,000 values, okay, from a population whose mean is 50 and standard deviation is 5. Okay, and that is from a normal distribution. Okay, we are taking a sample. Fine. So now our sample have 1,000 values. Okay, 1,000 values, but our mean will be, very near to what? The population mean. Okay, but it might not be exactly 50. Getting? Sample will represent the population, guys. Okay, it means it will be almost the same. Fine, but it might not be exactly the same. Okay, it might be almost the same. So that's why when you see, I'm from a population of, these are population parameters, right? So from a population whose mean is 50 and whose standard deviation is 5, I am taking a sample of 1,000. Okay, so and if you see the sample mean, it is 49.8. Okay, it is almost same as population. Okay, very minute error. Getting? Okay,
Yeah, Santosh.
or if you take, sometimes it will be 50.005. Okay, randomly it is taking 1,000. So if I run this again, 50.07. Okay, it is not exactly 50, but it is almost. Okay, it is almost. Okay, 50.12, as you can see. Okay, 50.03. Okay, so it is creating 1,000 samples from that population, which will almost similar. Fine. So with those 50 samples, fine. If you try to visualize, okay, it looks like a normal distribution. Fine. So it look like a normal distribution. Agree? So with this, what you can try to do over here is, okay, so these are the from Skype.stats. Okay, so you can create the distribution part also. Okay, right. So, but I will show you the easiest way. So once you have this sample, right? Okay, so once you have this sample, okay, 1,000 values generated, so you can assume you can assume, okay, this is a normal distribution. Okay, this is a normal distribution. So see here, we what I'm see try to understand here. I have wantedly took the normal distribution, okay, just to show you. Okay, but suppose you are having roughly like 1,000 values and you have plotted the histogram. Okay, and this is some continuous variable. Okay, as per our kernel, okay, parametric density estimation, okay, based upon the observation, if you feel, okay, this is this is looking like a, this is almost similar to a normal distribution. Okay, then you can assume, okay, that our this continuous variable, okay, is is a normal distribution. Okay, we can assume that this belongs to a normal distribution. And you can try to draw, for example, if you pass it to a what seaborn in seaborn. Okay, you have distribution plot. Okay, and if you just plot the, if you pass a sample, so whatever the sample you have to, okay, so it will give you, yeah, so if you see here, yeah, so as you can see, seaborn will also give you the graph. Okay, if you just pass the sample, so it will tell you the distribution where it is falling into. Fine. So by this graph also you can clearly see that it is almost following a normal distribution. Agree? So if I just run it again, okay, let me take it over here itself. Okay, see guys, okay, I'm taking, see now 49.9 I got, because it's the sample. Okay, fine, it might be some distribution, but using seaborn, okay, you can clearly see it is almost a bit skewed. Okay, as you can see here, it might be a bit skewed, but fine, but this can be considered as a normal distribution. Okay, so once you assume, okay, once you are convinced from the this graph, okay, this graph is looking like a normal distribution. Okay, if I could just run it again, yeah, this is okay. So if you can assume that now this is normal distribution. Okay, so now what you can do, you can use all the formula. Okay, you can use all the formula and rules and regulations that are applicable to normal distribution to your continuous random variable now. Okay, so with that you will have lots of details already available. Like there will be some symmetry, there should not be any skewness. Okay, this much amount of the data will be falling below this quantile. Okay, above 50 quantile or median, there should be half of the data. Okay, like that, what all rules and the what do you say, the principles that are applicable to the normal distribution, you can apply to our distribution also. Okay, because even though we don't know what type of distribution this is, just you can try to assume by this graph, okay, using the seaborn, okay, and also the histogram in the background. So you can try to estimate, okay, okay, this is looking like a near to normal distribution. Okay, so you can assume and you can carry out your process. Agree? So that is how you do with the parametric density estimation. Okay, is it clear, guys?
Yes, sir, clear.
Okay, fine. Now, second thing is non-parametric. Okay, see here. Second thing is non-parametric. Here, we don't assume any underlying distribution. Fine. So we don't know, we cannot assume any underlying distribution. So if it is, if the graph is like this, guys, just try to understand if the if you are seeing something like this, if you are continuous variable when you plot the histogram, if it is looking like this, you can obviously, okay, at least if not now, after a few classes you will just get a visualization in your mind. It is looking like a normal distribution even before plotting with the seaborn. Okay, you can just assume, you can visualize, you can clearly see that it is a normal distribution sort of thing. Okay, but in some cases, if the histogram is not following any normal, any famous probability density functions like normal, exponential, Poisson distributions, there what we are going to do, we cannot assume anything, right? Here we cannot assume anything. Then how we are going to come up with the distribution? Okay, that we are going to study. Okay, so for that we need to go for non-parametric density estimation, or also called as KDE, kernel density estimation. Okay, it's called kernel density estimation, guys. Fine. So here what happens, you see. So I'll just give you an idea how we are going to do here. So here, let's say you are having some points. Okay, let me just quickly take some. Yeah. So you are having, let's say, 1, 2, 3, 4, 5, 6 points out here. Okay, and here you have some, okay, some probability. So you have drawn here. So in the middle you have, so in between here to here you don't have anything. So that's why it is left blank. Okay, and again you are having some values over here and some values over here. Okay, so that's that's how its histogram is looking like. Fine. But now if you want to get this graph, the blue color graph is what we want to draw. Okay, we did not have that graph. Okay, how to draw that graph, how to get the probability density function or probability density distribution. Fine. So what is a continuous variable is called, guys? It's called, where did we go? Yeah, probability density function. Fine. So probability density function, how to draw how to draw this graph for this continuous variable when you cannot assume. Because if you see guys clearly, it's bimodal. That means what? You can clearly see it's a graph like this. Okay, and something like this. Okay, so you're having two modes. That's what it's called, bimodal, right? So it's not any famous distribution. Okay, we don't have any famous distribution. It's not normal, it's not exponential, it's nothing. Fine. Then how we are going to draw this? Okay, using these points. So here we don't assume any underlying distribution, guys. So instead what we do, we try to create a Gaussian distribution for each point. Okay, we try to create a observe here, guys, it's very interesting. See, we try to create a Gaussian distribution for each of this point. Okay, assuming that each point is a mean. Okay, that means what? See here, just observe. If I could just enlarge this. Okay. Yeah, see guys, what I'm saying for each point, assume that that point itself is the mean, and draw a normal distribution or Gaussian distribution. Okay, so that means what? So if you see this point, only focus on this point. Okay, assuming this point as the mean. Okay, so for example, let's say you are having a point over here. Okay, assuming this as the mean, if I want to draw a Gaussian distribution, that means normal distribution. Fine. So how I'm going to do? How does a normal distribution look like, guys? See, normal distribution look like this. Okay, bell curve. Fine. So where will be the mean? Mean will be here. Fine. Mean will be here. So now we are doing the reverse. Here we already have the graph, and mean will be here. But here, if you know the mean is here, if you want to draw a graph around that, okay, that means what? It will be like this. Agree? Assuming that this point is the mean, draw a Gaussian distribution above it. Fine. So similarly, if you see how many points are there? 1, 2, 3, 4, 5, 6 points are there. Okay, and you have 6 dotted red color graphs. Okay, distributions. For the first one, if you see this one, are you able to see? There. Okay, here this is the mean. Okay, this is the mean, and this first dotted line is there, right? This is the distribution I have assumed for this dotted line. Clear? Now, if I take some other color, let's say this. For the second one, okay, for second one, I will just okay, this is the mean, and if you see the second graph, fine, that is the Gaussian distribution I have drawn for this point. Fine. Getting guys? And for this point, this is a distribution where this point is the mean. It will be at the almost middle. Fine. For this point, this one, for this point, this one, for this point, this one. You have 3 more graphs. Okay. So total 6 points, 6 graphs. So here we are not assuming any underlying distribution. Instead of that, what we are doing, we don't know. Just by looking at this data, I don't know what type of famous distribution I should consider. Instead of that, I will consider each point as a mean. Okay, I will just assume each point is a mean, and I will draw a Gaussian distribution for that. Fine, you will have as many number of Gaussian distributions as the number of points. Fine, is this clear, guys? How did we draw this distributions? Okay, so we are going to, yeah, so for assuming each point we are going to draw a distribution. After that it's simple. So if you take this point, okay, if you take this point, fine, so if you see wherever it is intersecting, okay, wherever it is intersecting, fine, so the value of, for example, if it is if you want to draw a point over here, okay, if you want to calculate over this point, okay, so that means you go here, okay, this is one point from the first curve, and if you go again over here, this is one more point for the second curve. Okay, for this point there are two places, two places where you are having the intersection with these curves. Fine. So the value of the actual curve will be the value of this one plus this one. Okay. So this plus this. Okay. For example, this is 2, this is 3. Fine. The overall value will be, you just go and put it over here. You will have a point over here. Fine. Getting? For this point, if you see, you are having 1, 2, 3, 4. 4 points. It is intersecting all the curves. Agree? Add all those and plot that, you will have some point. Okay. For this point, if you see, okay, this is 1 point. Okay. And if you go, this is another point. Okay. Add these 2 points. Okay. It will go and give you some point. Okay. So like that, for this point, if you see, it is, you are having intersection over here, and there is one more point over here. Okay. Just go and point, add those values and give. So like that, you will have all the required values of y that is coming from all these distributions. Okay. Okay, guys, did you get that? So first you need to assume that each of the point is a mean, and you need to draw a Gaussian distribution. Fine. After that, just add the y values. Okay. Wherever, if you want to have a y value, okay, at this point, how did we get this? You need to see how many graphs are available in this horizontal line, okay, and add all those y values. Okay, so here if we're having 1, 2, 3, 3 graphs are there. Okay, each of these graph will have y value. Okay, the corresponding y value. Add all those y values, and you are going to get the you're going to get what? This corresponding y value. Fine. So if you see, that's why if you see where we are getting the peak value, here you are having the peak value. Why? Here there are, see, here also there are three graphs intersecting. Here also you can see three graphs intersecting, but here the length of y is high. Okay, the length of high is y, sorry, high. Fine. So that's why, so if it is 5, if it is 6, okay, if it is one more 6.5, so if we add all those, you will get a bigger y. Here you will have very small additions, so that's why you will have a smaller actual y. Okay, so that's how you need to plot the combination of all these values, okay, as a dots. And once you connect the dots, you will have this type of distribution. Okay, based on this, now this will be your probability density function for your continuous variable. Okay, and here we are not assuming any underlying distribution. We are just trying to come up with the distribution by just kernel density estimation. Okay, we are just estimating that each point could be in Gaussian distribution. We are trying to draw things above it, and we are trying to add the intersection points and coming up with the distribution. Is this clear, guys? Are you able to understand the way how we did this?
Yes, sir.
Karthik? Okay, fine. So, but here there is one point actually. So when I say we are drawing a Gaussian distribution, okay, or a normal distribution or Gaussian distribution, fine. So for any distribution, actually you need two things to draw, guys. Okay, you need two things. One is mean, one is a standard deviation. Okay, one is mean and one is a standard deviation. Okay, but now here I have just said that we are considering this point as the mean. Okay, and we are drawing a distribution. We got the mean, that's fine, but what about the standard deviation? Okay, what about the standard deviation? And what is the importance of standard deviation? How does will it affect the graph? We'll try to understand. See, what is standard deviation is, what is the spread of the distribution? Standard deviation is what? Standard deviation is just coming from the variance. Variance is what? How much the each value is varying from the mean. So indirectly, standard deviation will give you the spread of the distribution. That means what? For example, if you are having, let's say mean is 2, okay, let's say you're having this number, this is 2, fine. Now with the same mean, see, try to understand, with the same mean you can draw n number of graphs. Agree? See, mean is 2 only, still mean is 2. Still mean is 2. You are able to observe, because for all these graphs, okay, for all these graphs, if you see, the mean is 2 only, fine. But are these graphs same? No, they're all different. They're all different distributions, but the mean is same. Now what is that making difference? It is the standard deviation. Now what is standard deviation? This spread, okay, the spread for this is very low. Okay, for the next graph it is a bit high. Okay, for the above one it is highest among all. Fine, the width or the spread from the mean is the standard deviation. Okay, okay, so that's why you just need two things to draw a graph, guys. One is a mean, one is standard deviation. Mean is like what is a center point, and with assuming that as a center point, what will be the spread of the data around it. Fine. So if I just say mean is like 1 and standard deviation is 5, so you can take some 1 as a mean, and this will be 5. Okay, this will be 5. Fine. So with that you can just draw a graph. Agree? So you need two things, mean and standard deviation. Okay, so but here, so obviously I think you are able to understand that standard deviation is going to affect the shape of the distribution. Fine. If the standard deviation is too low, what will happen is the standard deviation is too low, the graph becomes thinner and thinner. Fine. It will become thinner and thinner because the spread is very much low. Fine. But if the standard deviation is high, then stand becomes fatter. The graph becomes fatter and fatter. Okay, because spread the more values are spread across the mean. Okay, no congested. But here it will be congested. Okay, and that is controlled by the parameter called a standard deviation. Okay. Similarly, here now coming back to our point. Here we are given some point. Okay, that's fine, and we want to draw a distribution. This is one point. Okay, assume this point is this, and I want to draw a distribution over around that. Okay, to draw a distribution, now we understood we need mu. What is mu? Mean and standard deviation. Now what is mean? This point itself is mean. Okay, we are assuming that each point will be the mean of the distribution, and we want to draw some Gaussian distribution. But what is the remaining parameter? That is standard deviation. So from where we are going to get the standard deviation? Okay, it is actually a hyperparameter. And what does hyperparameter mean, guys? So which means you can experiment with different parameters. Okay, so you will understand about hyperparameters very well when we are discussing machine learning concepts. Okay, but as of now there are two types of things. One is parameter, one is hyperparameter. Parameter is a fixed one, you cannot change it, it will come along with the function itself. Okay, but hyperparameters are those things which you can play around and come up with the best possible value. Okay, so here also standard deviation. Okay, now if you say mean is a parameter, we are considering mean as a parameter. You are not going to change because these are the values given, and we are just considering that point as a mean, and that will be a parameter. Okay, but standard deviation will be a hyper parameter. Okay, it is hyper parameter. Okay, that means this is not given, you can assume some values. Based upon the assumptions, the outputs will change, and you can decide with the best possible output. Okay, so now just like that, if you assume in our case also, if you the means are fixed, okay, but coming to standard deviation, if you take greater standard deviations, okay, if you take larger standard deviations, okay, for example means are fixed, right? So if my the graph which you are seeing over here, the blue color graph, okay, for that let me assume I have considered standard deviation of 5. Okay, but now that means what, this width, guys, for each and every graph, okay, for each and every graph the width is, I am considering it as 5. Okay, so that is resulting in this graph. Now if I take standard deviation equal to 2, fine, so you will have this, but it will be very thinner. Agree? That means what, this graph, this red color graph now become something like this. Okay, like this. Okay, like this. Fine, all this will become and this will also become a little thinner. Getting, guys? Now if I take standard deviation equal to 10, okay, each of this graph will be elongated. Okay, and the final graph will also be a bit spread out. Okay, trying to understand, because this graph is just a resultant of this individual small graphs, and these small graphs are coming up with two values, mean and standard deviation. So if your mean is fixed, if you're playing playing with the standard deviation, right, if you're playing with the standard deviation, the graph also changes its shape. Okay, if you take smaller and smaller standard deviation, the graphs become thinner and thinner. Okay, it will be like this. If you take big standard deviation values, you will have a bit elongated value. Okay, so with that you can play it, or you can take some different values, or mostly you can experiment with different values, and you can try to have a probability density function of your distribution. Okay, is a concept clear, guys? At least logic wise, are you able to understand how we are able to draw the distribution of this continuous random variable, where using the non-parametric, we did not assume the underlying is any normal or not. We're just going with the kernel density estimation. That means we're estimating the density around each point, and then we are trying to come up with the distribution. And also we are playing with the standard deviation and seeing how the distribution might change as we change the standard deviation. Please let me know, guys, if this is clear. If it's not clear, you can tell me, but are you able to understand the concept?
Yes, sir. Clear.
Okay, fine. So is it confusing, Meghna? Is it confusing PMF and CDF, or is it clear for you?
No, sir. Clear.
Okay, fine, great. Now we will try to see, but see, all these are theory, right? So in practical, you don't need to actually draw this. Okay, this is just as we are studying from the basics. I am just telling you from the first principles. Okay, but while we are doing the coding, right? So you will see there are already predefined built-in functions which will give you the direct graphs. Okay, but always it's important for you to understand. Okay, to have the clarity, like what is exactly what is probability distribution, what is PMF. Okay, it is stated the discrete part, and also how to draw the PMF function. Fine, yesterday we are seeing, right? So how to draw a PMF function. Okay, this part, and how to draw a CDF for that. Fine, and also then what is PDF, I mean the probability density function for continuous variable. Agree? And then why we are getting, why it is called the probability density, not the probability in the probability density function. Fine, because that is the area, so that's the density. Fine, so it will give you some value between the range. Okay, but it's not the actual probability, but it is a probability density. Fine, because the actual probability for any given single point is 0 in the case of probability density function, because it's a continuous random variable. Okay, I'm just repeating, giving you a recap. So the exact probability value, if you take for any given value, the overall possible outcomes are infinite. So the at any single point you take, the value will be 0. So that's why you cannot have a direct probability. You will have a probability density function. Okay, so any value you take, that will give you a probability density. Okay, and using the area you can calculate the probability. Fine, so after that, if you want to draw a PDF, we have seen the two ways. One is parametric and non-parametric. Fine, in parametric we'll just assume that it is a underlying distribution, could be following some famous distribution, and we'll try to use all those formulas. But in some cases you cannot do that, and that will give us the non-parametric, where we'll try to use the kernel density estimation, and we'll try to assume and try to draw the graph around that point. Okay, so I hope we are good till this point. Fine. So now finally we'll try to see something called as CDF of a PDF. That means yesterday we have seen cumulative distribution function of a PMF, right? So now how to do what to do with the PDF, probability density function. Okay, I'll just try to explain this graph. Okay, see guys. So here, okay, see here. So let's say this is a PDF, probability density function, and this is a cumulative distribution function. Okay, of this function. Okay, and how to understand this? See, here there are -3, -2. Okay, this is some normal distribution. Okay, this is one type of probability density function, and this is a normal distribution. Okay, here if you see, this is a corresponding cumulative distribution for this. And how you can understand this is, see, what is cumulative distribution function, guys? It will tell you all the values less than or equal to a given value. Agree? So if you are looking for some 3, okay, if you're looking for 3, it will tell you all the values for where x is less than or equal to 3. Fine. Yesterday we are able to see you remember, right? I'm just trying to give you a recollect. Okay, this is a cumulative frequency. Okay, yesterday I've shown this also. Fine. So now, yeah. So now if you try to understand the cumulative function over here, see, it is saying, okay, I'll just take you I'll try to give you one example. Okay, now you will understand what is the area. When we are saying the area, so it is giving the probability uh, density, right? And here you are having the actual in the cumulative, it will tell you the value less than or equal to the given value. Okay, see, you'll understand. Now if you see, let's say I am focusing on 0. Okay, I'm 0. Okay, now if you see here in the overall graph for 0, okay, for 0, if I want to say what is the probability, okay, what is the probability that a given random variable will be found for 0, okay, will be found at 0. How much it is, guys? It is 0.4, okay, from this probability density function. Agree? But now coming to cumulative distribution, guys, coming to cumulative distribution, what does that mean? When I ask for 0, what does that mean? It is x is, can you tell me? X is in cumulative, uh, if I ask for 0, what it will give you? Can you guess? Okay, so it will be x equal to less than or equal to 0. Agree? Guys, are you following?
Yeah,
In
Sandesh.
see, when I am looking for a particular value, okay, in probability density function, you will get for a particular 2, okay, but in the cumulative, you will have x for x will be less than or equal to 2. That is a word of cumulative, right? So it will give you probability of all the values less than or equal to the given value. Okay, so here also, if you see for 0 over here, the probability is, okay, the 0.4, but cumulative distribution of 0, okay, that means cumulative distribution of 0, if you see over here, okay, that means what? Less than or equal to 0. Okay, now for less than or equal to 0, what are these are values, these are values. Okay, now see, if I want to find out what is the probability that a given random variable is falling between -3 to 0. Okay, are you getting?
Yeah.
Huh?
Yes.
Yeah. So here, when for the cumulative distribution, if you're looking at 0, what does it mean? It is looking for x is less than or equal to 0. That means what? It is giving you the probability that some given random variable is falling between 0 or less than 0. That means here our less than 0, the minimum range is -3. That means indirectly we are asking what is the probability that a value will be found between -3 to 0. Right? 0 means less than 0. That means -1, -2, -3. Okay. This probability I want. This probability I want. How will I get the probability from the probability density function? What is the probability?
You mean area between -3? That's what you.
Correct. Perfect. Okay. So here the area between -3. Okay. This one will give you the probability, right? So that is the thing which we have studied, right? So over here also I was saying, if you want to find out the probability that a given random variable will occur between -2 to 2, what did we do, guys? We just considered the area between -2 to 2. This area, okay, if you want to calculate, you can calculate, or if you don't want to calculate, you can just integrate this will have some function. Okay, you can integrate this function from -2 to 2 and just solve the equation. You'll get some value. Okay, that value is the probability that this continuous random variable will fall between -2 to 2. Correct? Same thing, because this random variable, there might be any value set of values in this random variable, right? Just to give a recap, if it is salary, lot of values are possible. Okay, but I want to just say what is the probability that what is the probability that salary will be falling between this range. Okay, and that will give you the area will give you that answer. Similarly, here, okay, over here, when I am try to understand, when I am saying what is the cumulative density, okay, of 0, that means what is the probability that a value will be found equal to or less than 0. Okay, 0 or less than 0. That means -3 to 0, because -3 our minimum value. Okay, that means what? From -3 to 0, what is the probability that I'll find a value? How you get the probability in probability density function? It is just the area. Fine. And how much this area? How much this area? The total probability is how much, guys? Can you tell me what will be the overall probability for any given concept?
1.
1. So that means area will also be equal to 1.
1.
1. So now with that, so can you tell me how much this will be?
0.5.
0.5, right? So this part, -3 to 0, the probability to find a value between -3 to 0 will be area between -3 and 0, which is half of this. So that means it will be 0.5. So that means if you see 0 and if you extend this, okay, and if you draw here, it will be 0.4, 0.6, it will be 0.5. Clear? So it is clearly saying the cumulative distribution function is saying that at 0, the value is 0.5. That means the probability that you are going to find, okay, the probability that you are going to find a value which is equal to 0 or less than 0 is 0.5. Okay, 0.5. That means 50% of chances are there to find a value in between this range. Getting?
Can you please repeat once?
Sure. See here. What is this simply? This is just it is telling you, probability density function is telling you the area is going to give you the probability. Simple. Let's not make it complex. What we are doing, we are just calculating the area. What is the area is giving you? Let's call it as probability. It is probability density, but fine, we'll call it as a probability. Okay, that means what is the probability? Okay, what is the probability that a given random variable will fall in between this -3 to 0? Okay, that is this area. If you are not getting, see, I'll just go back one step again. So yesterday we have seen what? We are seeing the dice example. In dice example, when we are rolling dice, 1, 1, 2, 3, 4, 5, 6 are the possible outcomes. Agree? Now, what is the probability of 1? 1 by 6. Similarly, for all the outcomes, 1 by 6. Agree?
Yes.
Fine. Now, what is the probability that I give? If you are asking for a single value, you are saying 1 by 6. Okay, but here I cannot go by a single value. Okay, because this is a continuous variable. Agree? There are a lot of values, infinite values. So I don't want to go by a single value. Here also, in discrete also, if I ask you, what is the probability that a dice will be between 1 and 4? First, let's try to understand here. Then we'll go here. I am rolling a dice. Okay. What is the to get the prob 1, it is 1 by 6, 2, 1 by 6, all 1 by 6. But now I want to know what is the probability that I will get a number between 1 and 4. That means what is the probability to get 1 or 2 or 3 or 4? What will be this?
I mean, you're asking discrete.
Discrete. Here only.
1 by 6 only.
No.
Uh,
For 1, it is 1 by 6. For 2, it is 1 by 6. But I want to know what is the probability that a number can fall between 1 and 4, 1 or 2 or 3 or 4. It will be sum of all probabilities, right? Because now the probability is increasing. Because here,
okay.
are you getting? When you are,
Yes.
yeah,
Yes.
see, I will, the maximum case is what? If I ask you, if I ask you, what is the probability that a number will fall between 1 and 6? What is the probability that a number will fall between 1 and 6? What is the probability?
Total is 1.
1, correct? Perfect. So when I ask you, what is the probability that a number, I'm rolling a dice, what is the probability that I will get either 1 or 2 or 3 or 4 or 5 or 6? What is the probability?
1 by 6.
No. See, let's not get confused. See. Meghna, are you on track? That's fine. We'll come back.
Yes, sir.
I'm rolling a dice. I'm saying what is the probability to get either 1 or 2 or 3, or I'm not asking individual probability.
Okay.
To
Okay.
get
Got it.
any of, I want any of this number. Any of this number I want to get. Fine. So what is the probability now?
1.
1. Agree? Because it is sum of each individual probability. That is 1. Because if you roll a dice, you are definitely going to get one of this number. So if you want to find one of this number, the probability is 1. Definitely you are going to get 100%. You are going to get. Agree? That's why the probability is 1. Agree? This is a maximum. Clear? Now,
Yes.
but if I ask you what is the probability if I get, okay, I'll write it as this. Okay, anyone you are happy. But if I ask you what is the probability, I just want 1. For only 1, what is the probability?
1/6.
Correct, 1/6. I just want for only 2, what is the probability? 1/6. Like that. For only 6, I want to see 1/6. Okay, clear? Now, what is the probability? I want to see 1 or 2 or 3 or 4.
Okay. I mean,
4 times
1
1.
by 6. 4/6. Yeah.
Correct. What is the probability? I want to see 2 or 3 or 5. 3 times 1/6.
Yes.
Agree? Agree?
Yes.
Are you able to
Yes.
understand the difference between this one, the overall probability, each individual probability, or a range of probability?
Yes, Santosh.
Okay, Meghna? This, if you understand this, then that will be easy. This is clear, right?
Yes, sir, clear.
Fine. Now, just I'm adding this concept over there. So here you are using the range. Because this is discrete, you can go for the individual probability. Only 1 you can find out, 2 you can find out, 3 you can find out. That's fine. But because continuous variable are infinite values, so there we go by the range. That means from 1 to 4, I want to find out from range of 1 to 4, what is the probability. Okay, getting?
Yeah. Yes.
Same thing if I go here. Okay, so I'm saying from 3 to 0, what is the probability I will get a value. Okay, just like how we have done this from 1 to 4, what is the probability? I will find a value. Okay, this is my range. 1 and 4 are my range. What is the probability that if I'm rolling a dice, my value can be seen between 1 or 2 or 3 and 4? You will sum up the probability. Fine, because you know what are the values you are going to get here, you will have a clarity. But in a continuous variable, okay, you don't know the values. Okay, you don't know the values. Fine. So, but that is a point here. You don't know the values, but your question is, I don't know what are my whole data set or what are my complete set of random variable. Because in discrete, this is your random variable 1, 2, 3, 4, 5, 6. In continuous, you don't know. It is like infinite. Fine. Any number is possible between the range, but I'm not interested in that. Just like how I'm saying between 1 to 4, what is my probability to find out this range? Here also I'm asking between -3 to 0, what is my probability to find out my random variable? I don't care what is the range of what all the possible values of my continuous random variable. I don't care. But my interest is between -3 to 0. Tell me the probability of finding that random variable. Getting?
Yes.
Okay. So that will give you the area. Area is simply you are adding each individual probability. Okay, just like how you are adding 1/6, 1/6 here. So in probability density function, you are going to add all the possible area under that. Okay, this area from -3 to 0, the area whatever you get, that will be the probability to find a random variable in between this range.
Okay.
Okay, just like how this 1, 2, 3, 4 means 4 times 1/6, 4/6. So now 4/6 is the probability that you are going to find a value between 1 to 4 when you are rolling a dice. 4/6 is a probability to find your random variable, discrete random variable between 1 to 4 is 4/6. Similarly here, the area is the probability that you will find your continuous random variable between this range.
Yes.
I hope it's clear now.
Yes, Santosh. But only thing is, here, I mean, complete -3 to 3, it's 1.
Correct.
So, it's -3 to 0, middle, I mean, correct in the half. That's why we're taking it as 1/2 or 0.5.
Correct.
But
Correct.
what if it is the area, like if you have -3 to, let's say, 7, -3 to 7.
7,
We
but
want
there is no 7, right? So the graph is ending at 3.
okay,
After 3,
okay,
there are no
then
probability.
okay, fine. In this case, -3 to I want 1 or
Okay.
-3 to -2. in that case, how we can say directly, like here we have midpoint, so we are saying like 0.5.
That's what the that's what the cumulative
Okay.
is giving you, right?
Okay, then fine. Directly we can find out from cumulative.
Right. So from -3 to 2 means what? If you are asking for -2, fine. That's a good question. So if you're asking for -2, see. Now when you are asking for 0, it is giving you what? It is giving you less than or equal to 0. Fine.
Yes.
Now when you are asking for -2, just give me a second. So when you're asking for -2, it will give you what? X equal to less than or equal to -2. Less than
Correct.
or equal to -2. That means what? From -2, the least point is -3. This area probability you are going to get, and who is going to give that? Cumulative distribution is going to directly give that. That means what? For -2, if you see, fine.
Yes.
-2, if you see at 3 it is 0. For -2 it is
Slightly
just
above.
small, slightly greater than,
Yes.
okay, greater than 0.
Yes.
And let's say if this is 0, this is 0.2, somewhere middle it will be 0.1, and it will be middle of
0.01. 0.01. Right. 0.02.
0.02, something like that. Okay. Now
Okay.
that is a probability that we are going to find a value
Okay.
between -3 to -2.
Okay,
Okay.
Santosh. Yeah.
Perfect. And you will understand if you take a bigger value, you will understand in a better way. See, let me take between minus till 2. Okay. If I am asking for 2. Okay. Plus 2. Okay. So if I'm asking, hey, what is the probability for to find a value? Okay. For less than or equal to 2. Okay. 2. That means what? This one. So less than or equal to 2 means what? 2 and -3. Agree? So this complete area.
Correct.
Okay. This complete area. Just don't touch this area above 2, less than 2, and all this area. This complete area is actually is giving you the probability, right? Probability of what?
Yeah.
To find out the random variable from -3 to 2. Fine. So
Correct.
that's exactly
Yeah.
the cumulative is telling you. And how much this? Roughly you can say, it is greater than 50, obviously, and greater than 75 also, some roughly. So that's why if you see here, this two, if you see the two here, okay, if you just sorry, okay, if you just draw here, okay,
Yeah.
it will be almost equal to 1, but not 1,
Yes.
somewhat less than. So
Yes.
this small portion which you see here, that is this portion.
Okay.
Okay. So from here you can clearly understand for 2, that means what? The overall range is itself -3 to 3. If I'm asking you what is the probability that the random variable you can find between -3 to 2, that means almost range I'm covering. That means almost area you will get. So that's why if you see the 2 will be almost 1. It's not 1. But if you ask for 3, ask for 3,
1.
ho gaya, pura. Okay, that means 1. That's why if you see for 3, it will be 1. So that's why yesterday also I told, if you remember, the cumulative distribution function will always have a maximum value of 1.
Yes.
Here also, if you see cumulative distribution function, so each individual, this is a case of rolling 2 dice. Each individual might have 2, 3 or different probabilities. Okay, but the cumulative is always adding up, adding up. The maximum will cover everything, and that is 1. Okay, for the PMF, even in the PDF also, cumulative might have, cumulative is continuously telling you the values which are less than or equal to that value, less than or equal to that value. And when you are having the 3, okay, when you are having the maximum value, obviously that should cover the complete probability. So 3 should cover the complete probability. Sorry. Okay, so that should cover the complete probability, and that will always give you the 1. Fine. But the importance of cumulative distribution over here is, okay, so you can directly find out the like the values of this from here. So if you see roughly 1 for 1, okay, I don't know how much this is. This is 8. That means 80% of the value. 80% of the value should be less than 1. Okay, so as you can see over here, so if you take this one and consider all the values above here, and if you just remove these values above 1, so this should be the 80%. So that means 80% of the values are, you can have a probability that 80% of the sorry, 0.8 is a probability that we are going to find a value between -3 to 1. Okay, because there is something left over here. Clear? Let me know, guys. Is it clear?
Yeah, Santosh. Fine.
Any doubts, Meghna? That's
No,
fine.
clear.
Clear, right? Okay. Perfect. So this is actually regarding the probability density function, guys, and the corresponding cumulative. Okay. So I hope it is clear. Okay. I just recommend you to just go through the class once again, because you will have more clarity. Okay. Fine. So with this, we have covered the basics of the distribution functions like PMF, PDF, which is basically coming from the discrete and continuous. Okay. After that, we are going to see all these distributions independently. Okay. So individually, you will have better understanding. And the first thing we are going to cover over here is you will start with the uniform distribution and we'll go to the normal distribution. Okay. But I recommend you through you to go through the class, because this fundamental should be clear for you. Okay. So that you will understand, this will be easy. Okay. Once you know the basic principles, everything is just addition of top of that. That's it. Those will not be any difficult. Okay. So we can cover tomorrow we are going to cover uniform distribution, and after that we are going to start with the the most important concept in the whole statistics, that is a normal distribution. Okay. So you're going to see normal distribution, and these are very small, very interesting, and also very simple, I would say. The or understanding the probability density function might be a little challenging. Okay. But I hope it is as much clear as possible from the class. But still, you go through the recording once. Okay. Just try to understand like how this is giving you the area a probability, how this is giving you the probability density. Okay. So that's why I'll just give you a, before closing, right, the end point, one important point I will tell you. If you observe we are doing the integration, right? So you can conclude that if you integrate a probability density function. Okay. Okay. If you integrate probability density function, what you are actually getting is you will get a CDF. Okay. That means what? From -2 to 2, from -2 to 2, okay, you are calculating the value. Okay. And if you are integrated from least value, that means I don't know what is the least value, I am considering it as -infinity. Okay. From -infinity to any value you want to take. Okay. That means what? If I ask for 2, what is cumulative distribution function do? It will give you value x is less than or equal to 2. Okay. Less than or equal to 2 means 2 and all the values below it. I don't know the minimum value, I'll assume it as -infinity. Okay. -infinity. So if you do this, that means if you are doing integration of a PDF function, that will give you a cumulative distribution function. Agree? Do you agree with me for this?
Yeah, Santosh.
Okay. Integration. So that means what? See, if you want to take only a specific piece of this, if you want to just cut this part, that's fine, that's your wish, you can integrate between only -2 to 2. But the actual nature of cumulative distribution is what? It will give you, it will by default consider the least value. It will start from, if you ask for 2, it will give from -4 to 2, or whatever this value from 2. If you ask for 0, it will give from here to here. Okay. So for that, you can consider it as -infinity. This is just a general notation, -infinity, but in the graph, whatever the value you are having over here, you can take that. Okay. Usually I'm taking it as -infinity. Okay. So if you are integrating this from -infinity to the given value, you'll get CDF. Okay. Now, interestingly, if you can think other way around, if you just reverse this out, that means if you do the differentiation, that means if you do the differentiation of CDF, what you will get? PDF.
Yes.
Okay. That means what? At a particular value, differentiation is what? At a particular value. Okay. That it will give you a PDF of that. If you take the integration, if you take the area and you add everything up till that point, that will give you a CDF. And if you do the differentiation of CDF, okay, that means a particular value at 2. Okay. That means what? It's very interesting. See, when I'm saying 2, CDF will automatically consider less than or equal to 2. That means what? You are integrating. That will give you CDF. But differentiating means what? At what value you have considered CDF? 2. That means if when you are differentiating, you will differentiate with only 2, only exactly at 2, not less than or equal to 2. Okay. That means you will get this particular probability at this point when you do differentiation. Okay. See, I'll repeat just once. When you are doing, when you are saying 2, when you just say 2, CDF will do what? CDF will automatically consider x is less than or equal to 2. Okay. X is less than or equal to 2, and it will just to integrate it with from what is our value? Okay, let's call it as some minus, sorry, what is this? Let me call it as 0. Okay. From 0 to 2, it will consider, and it will do the integration, and it will consider all the area, and it will give you what is that CDF. You will get CDF. Okay. Now, when you're doing differentiation, at what value you are doing differentiation? First of all, at what value did you start CDF? You started at 2. Because it is CDF, you are considered less than or equal to 2. But now when you're doing differentiation, you will only differentiate at particular value x equal to, here x equal to 2. When you do that differentiation, okay, you will get exact value at only that particular point. You will not consider area. Differentiation will only give you that particular point to what is the probability. Fine. Now Now if you start integrating, then all this area will come and that will give you the CDF. Okay, integration of function will give you CDF, differentiation of CDF will again give you PDF. Okay, you don't worry, you don't need to do integration differentiations. Okay, don't get scared, it is just a behind the scenes what is happening, I'm just telling you. Okay, so you have everything, libraries available, fine. So that is the beauty of I would say Python. Okay, because you have the theory, you'll understand theory, but again you don't need to do it from scratch, you already have predefined built-in functions. Okay, but understanding the behind the max is always helpful, even from your interview point of view also. Okay, so this is I would say this will conclude. Okay, this will conclude the point, fine. So fine guys, so that's all from my end. Okay, have good understanding about PDFs and till PDFs, right? So PMF, PDF, discrete, random, continuous, all these have good understanding, make some notes. Okay, so come prepared from tomorrow's class. Okay, so because tomorrow we are going to go into the actual examples. Okay, these are general topics, umbrella topics, but now tomorrow we are going to touch each and every of this uniform, normal, everything. Okay, then you'll have a better understanding. Okay, so yeah guys, that's all from my end. I hope the class is clear. You can let me know if you are good or any doubts.
Fine, Santosh.
Okay. Yeah, I hope it's also good with you, Meghana. Okay, fine. Uh, that's all from my end. Okay, let's meet tomorrow. Okay, let's join on time. Fine. Thank you so much, guys. Let's meet tomorrow. Bye.